So now the trajectories have been computed, and by default you get a plot like the one shown in the graphics window, where you get a little dot representing each particle, and the color represents an expression which I'll explain momentarily. So in this case, you only see the particles at the final time step, but we actually want to see how their trajectory changes as they move through the coil assembly. So if we go to our particle trajectories plot, we can select to see lines instead of points. And now we can see how the particles come in from this inlet, they're focused by the magnetic field, and then they begin to diverge as they move away from the magnetic field lines. By default, they're colored by an expression which corresponds to the norm of the particle velocity. And we see that the particle velocity basically doesn't change if we look at this color scale here. And that's consistent with the expected value, because magnetic fields can't do any work on charged particles. So we expect their energy and velocity to remain unaltered through the model. And they essentially do to within numerical precision. We can change the expression for which the trajectories are colored. So we can change it, we can plot, for example, components of the force. We can plot, for example, the x component of the force. We could plot the y component of the force, for example. And we can also color the particle trajectories with any expression from the magnetic fields interface as well. So we can, for example, color the particle trajectories according to the magnitude of the magnetic flux density. So one way of visualizing specifics of what happens along particle trajectories is to use something called a Poincare section. And we can do that in our model using the data sets. So the first thing we need to do is to define a cut plane. And this cut plane corresponds to a Poincare section, and then from this we're going to create a Poincare map. And this is going to allow us to see how the electrons focus and then diverge at different points in the modeling plane. So the first thing I'm going to do is to define a cut plane in the XY plane and set its position to -6 millimeters. So we can see the cut plane here in the graphics window. I want to also create two more cut planes which we can use to define Poincare maps on, and a quick and convenient way of doing this is to use the duplicate option in the context menu. So I'm going to duplicate that and change the z coordinate, and then I'm going to do it once more and again change the z coordinate. So now we can define 3 Poincare maps and look at how the trajectories change within the cross-section of the modeling domain. So the way I add Poincare maps is to right-click on Results and select a 2D plot group. And then if I right-click on the 2D plot group, under More Plots, we see there's an option here called Poincare map. So if I select a cut plane, in this case cut plane 2, then the Poincare map basically plots the intersection of a particle trajectory with the cut plane and places a little dot there. Now because we simulated so many particles, it's kind of hard to see, so we want to, for example, cut down on the radius scale factor. So the x and the y-axis represent the x and the y-axis in the 3D model, and the dots represent the location in space where the particle trajectory cut through. So I can duplicate this and assign it to these different cut planes, and then we can see for our second cut plane, this corresponds to the focal point of the lens, so we can see how much the area of the particles has shrunk. it's essentially shrunk from a radius of 2 millimeters to 0.5 millimeter. We can also add a third Poincare map and see how the cross-sectional area of the particle trajectories has changed as they move away from the magnetic field. Up to a radius is up to around 7.5 millimeters here. So this gives us more of a qualitative picture of how the particle trajectories are changing in the XY plane as they're moving through the modeling domain. One other thing we can do with the particle trajectories is compute averaged quantities over all particles. So if I right click on data sets on the more, I can choose average. And if I set the data set to the particles, then we can then plot average quantities over all particles versus time. So the way I do that is I add a 1D plot group and I choose my average data set. Then if I add a point graph, I can choose any expression I want and average this over all the particles and plot it versus time. So this allows us to plot, for example, the average value of the magnetic flux density as seen by the particles versus time. So if we examine this, it kind of makes sense. Initially the flux density is quite small. As the particles move closer to the coil carrying the current, the average magnetic flux density that they see increases. This focuses the particles to a focal point, and then after this they begin to diverge. So there are many different options under results which you can use to access physical quantities of interest with respect to particles, albeit information about particles themselves, their trajectories at certain cut planes in the model, and we can also integrate and average quantities over particles.